work on 4.3. And it's a pretty big chapter, 4.3. It's got a lot of important ideas in it, and there's several big ideas and concepts. So we want to definitely take our time to work through that. So what 4.3 is giving us is it's telling us about what a function looks like from its derivative. So what can you tell about a function from its derivative? And we already actually know some of these ideas already, but this is kind of formalizing what we already know. And the idea is that if the function looks like this, then we know roughly what the derivative is at these points, right? The derivative here, because the slope of the tangent line is positive, the derivative would be positive, right? And up here where it's flat, we know the derivative is 0, right? So we kind of can use the shape of the function to tell us the derivative, but we can also use the derivative, right, to tell us the shape of the function. So it's maybe a slightly different perspective on things. And here's our definition. It's in the book. It says if f prime of x is bigger than 0 on an interval, then f of x is increasing on that interval. So the idea is that if the derivative is positive, then we know the function is increasing. And we've, like I said, we've usually thought about the other way. We thought about if the function is increasing and its derivative is positive, but it turns out they're one and the same, right? So if the derivative is positive, that means the function is also increasing. And of course, the same thing is true for decreasing, right? If f prime of x is less than 0 on an interval, then the function is decreasing, right? So same basic definition. And so based on that information, we can now figure out where a function is increasing and decreasing. For example, so here's a function. It's a cubic function. And the question is, where is it increasing? And then, of course, also, where is it decreasing, right? Because it's one or the other, or else it's flat, right? 0. And this is a question we couldn't really answer before we had calculus, or these ideas of the derivative. If you had seen a question like this in college algebra, you could have maybe figured out where it had zeros, right, or x-intercepts, but you wouldn't have been able to figure out where it actually goes from increasing to decreasing and back again. So this is kind of powerful information, or at least hard to find information otherwise. And the idea is just this: increasing, decreasing is really a question of what the derivative is. So I'm going to start by finding the derivative. It's a nice polynomial, so I like taking its derivative. And now the question becomes, when is this derivative function positive and when is it negative, right? Positive is going to give me increasing. And with functions like this, the key spot are these critical numbers, because the critical numbers are where the function can change from increasing to decreasing, right? Or positive to negative. So in other words, this function is positive somewhere and negative other places. And the only spots it can change are where this function is 0, right? Because that would mean it's like going through the x-axis, or where the function has some sort of hop or jump, right? So here it goes from positive to negative, here it goes from, here it goes from negative to positive, here it goes from positive to negative. And so those spots where the function is either 0 or undefined, those are what we call the critical numbers, right? That's where the derivative is 0 or undefined. So this is really the same kinds of steps we were taking back in 4.1, where I have a function, I want to figure out where it's 0 or undefined. I actually think I made this kind of harder than I would have liked. So let's, well, we can just work with it because, you know, this is a quadratic. I wanted to make it something that would factor. I think I kind of messed it up. Yeah, I don't think I can get to -6 there, right? So if I can't do that, then I would use the quadratic formula. B squared minus 4ac all over 2a. 6 plus or minus the square root of 36 plus 96. 6 plus or minus the square root of 134 over 6, which is, you know, these two numbers here. You know, the square root of 134 is like a little bigger than 12. So I have 6 plus 12. So this is approximately 3, and 6 minus 12 is -1. So like real roughly, those are these values. And so those are the spots where this is equal to 0. Those are the spots where the derivative could change from positive to negative. And so, you know, you could analyze this one because it's a quadratic and you know what it looks like, but lots of our other functions, we won't know what they look like. If it has natural logs in it or it has sine of x times x, we don't know what those functions are. So this strategy of finding where the function is 0 and then testing. And what we're going to do is, you know, this function is defined for all numbers. So I'm going to use these critical numbers. Let's just say 1.1, just so we're clear it's not a, maybe 3.1. So notice what I did there is I took the whole interval from -infinity to infinity and I chopped it, right, at each of these critical numbers. I don't know whether it's positive or negative on this interval, but I know whatever it is, it can't change because it can only change at a critical number. So what I want to do then is I want to test. I want to pick some value in this interval, like -5. Here I'd probably use 0. Maybe here I use 5. And I'm going to check the derivative at each of those values. And I'm only interested in, is the derivative positive or is the derivative negative? I don't care what actual value it is. So we put in -5. Remember, I'm checking whether derivative is positive or negative because I'm interested in this, increasing, decreasing. So I put in -5, I get, you know, 25 times 3, that's 75, and then the -5 makes that +30. That's certainly much bigger than 8. That's going to be positive. When I put in 0, I get -8, so that's negative. And when I put in 5, it turns out this 75 is much bigger than that negative, so that's also positive. So this is really the sort of information, and people set up these sign charts slightly differently. So the book, if you look at an example, it kind of, well, it kind of sets it up on its side, like it puts the intervals over here, then lists the test values and the values across the top, and it's the same thing, just transposed. what's important though is that we can interpret this result and say that these then are my two intervals where my function is increasing because its derivative is positive. So the answer to this question, where is this increasing? It's increasing on the interval minus infinity to minus 1.1, union the interval from 3.1 to infinity. And to be honest, I really should put those values in there. I just didn't want to complicate it by having to write that down. Questions? Any questions about this first example? You know, the algebraic and calculus work here is to be honest not that hard. It's a very easy derivative to find. It's just a simple quadratic formula to find these answers. We're not really doing any complicated algebra, but it's a longer process. It's using a bunch of different steps and ideas and concepts. So it is, in that respect, not straightforward, right? It's not a one-step kind of thing. You got to work your way through and understand what you're doing at each of these steps in order to be successful with these. Okay. Any questions? Notice what else this information tells us about the graph. What it says here is that from minus infinity up to minus 1.1, the function, the derivative is positive, so the function is increasing. Now, I don't actually know where that is, right? It could be increasing up to here, or it could be increasing up to here, or somewhere in between, but wherever it is, it's increasing all the way up to minus 1.1 or whatever this value is. And then right at that point, it changes, and then it's decreasing all the way down to 3.1, right? 3.1, again, it changes, and it begins to increase again. Now, like I said, I don't know exactly where this stops, right? Or how fast it's decreasing. But I know that it changes at those two values. So notice what that's telling us. If the function goes from increasing to decreasing, as long as the function exists there, right, that critical point, remember, has to be, if it's really a critical point, it has to be part of the function. So if this is a critical point and the function goes from increasing to decreasing, this point then has to be a relative max. In the same way, this point is going to be a relative minimum. So by analyzing the increasing, decreasing, not only do we get the shape of the graph, but now we're actually able to categorize whether these critical points are relative minimums or maximums. We weren't really able to do that in 4.1. We could test the critical points and kind of, sometimes it would tell me it was an absolute max or absolute min, but sometimes it wouldn't know. Excuse me. But now, knowing about increasing and decreasing, now I know what these critical points are, right? This tells me this first one is a relative max and the second one is a relative minimum. And this testing or observation here is called the first derivative test. And just, so we're clear, it's sometimes a confusing name because it's like, well, isn't kind of the first derivative test? This is actually kind of not. This is just telling us increasing, decreasing. The first derivative test is looking at the critical points and comparing that to the increasing, decreasing, right? To see if we have a relative max or a relative min. So the first derivative test is a way of determining whether we have a relative maximum or minimum. And so the answer to a first derivative test would be, yes, this critical point is a relative maximum. Very different than the conclusion to this question. Any questions there? Let's see when there's, yeah, I'll have to come back to that. So again, it's written in the books. Maybe I don't want to just, well, here, just show you. Actually, I have the book right here. Like that. So notice a couple points here. C is a critical number of the continuous function f. So those are both conditions. If your function's not continuous, then the test doesn't necessarily work this way, right? And C has to be a critical number, which means, you know, the function has to be defined there. So it doesn't work everywhere, but if you have that, if the derivative changes from positive to negative, then f has a local maximum. And that's exactly what we saw. I mean, they're showing it here, right, from positive to negative, but that's what we saw in our little graph too. The derivative changes from negative to positive, then it has a local minimum. Don't memorize this like, you know, negatives and positives and things like that. You want to just think about what it's telling you, right? Negative to positive means decreasing to increasing, and visually you can see that gives you that local minimum. And then if it doesn't change, so in these second two examples, right, it goes from positive to positive and negative to negative, then there's no local min or max. It's still a critical number, right? The derivative is 0 there, but it doesn't count as a local minimum or a local maximum. So yes, and that's diagnosis. This is what I would say too. It is easy to remember the first derivative test by visualizing the diagrams like here. Don't memorize it in this red box, right? Just visualize the diagrams. That's going to work for anything that we run across. So if the question asks you to find the relative minimums and maximums, you basically do all of the same work that you would for increasing, decreasing. And you get to this point, and here then you can determine increasing, decreasing, or relative mins and relative maximums. So they're very connected, those two problems, because if you know one, you know the other. Well, if you know increasing, decreasing, you know the relative extrema. Knowing relative extrema doesn't actually always tell us anything about increasing, decreasing, but the work is the same. Okay, no questions about that. I'm hoping that's a good sign. A brilliant explanation, or the hard work that you've already put in, perhaps. Okay. So the second part of this chapter, it's good. I mean, it definitely can be straightforward. It's not, like I was saying, it's not a huge idea or hugely complicated. It's just kind of keeping in order to the problem. Now it starts to get a little bit more complicated if we ask the question about f double prime of x. So the first derivative tells us something about the function, increasing or decreasing. What does the second derivative tell us about the function? Well, remember that the second derivative is just the derivative of the first derivative. So f double prime, this tells us if f prime of x is increasing or decreasing, right? The derivative the derivative is the slope, but it's also a function. And so its derivative, which is f double prime, tells us whether that previous function is increasing or decreasing. That's what the derivative does. That's what we just saw. And so, so that's certainly true. But remember, we're interested in what it tells us about f, the original function. So if f prime is increasing, that means the slopes, f prime is the slope of f prime, the slopes are increasing. They're getting larger, right? Or they could be negative and getting larger, but they're getting larger. They're moving upward. So what that means is if f double prime is positive, that implies f prime of x is increasing. And that means we have something like this. If the slope started out negative, they have to be getting larger. So this is a large negative here, that's a less negative here, it's like 0. If they were positive, they'd have to be getting more and more positive. If, on the other hand, f double prime of x was less than 0, that implies that f prime of x is decreasing. So if it started out going positive slopes, they'd have to be getting less and less and less and less till they're 0. And if they're 0, they have to be getting less and less and less and larger and steeper and steeper. So we would get this kind of shape. So notice that f double prime of x can be positive and the function could be decreasing or increasing. So it is not about whether the function is increasing or decreasing, it's about whether the slopes are increasing, right? Or the slopes are decreasing. So this is a separate kind of measurement than increasing and decreasing. And what we call it is concavity. So this, if the second derivative is positive, then we say this function is concave up. And if it's negative, we say it's concave down. This is an important extra refinement to what our function is doing. And my standard example, if you watched the lecture, you would have seen this, right? Is that if I tell you the stock, this particular stock is increasing, it sounds good, but it may not be what you think. If you're an optimist, you imagine increasing is looking like this, right? And you'd really like to buy that stock because it's going up and up and up. But increasing can also be like this. This stock is also increasing, but of course it's not nearly as desirable, right? So just knowing that something is increasing doesn't really tell us exactly what's going on. It tells us something, but I would like to know a little bit more, and that's what concavity tells us. So this is increasing and it's concave up. The slopes are getting larger. So that's good, right? The concavity tells me that this is sort of changing in a way that's positive. Here, this is still increasing, but it's concave down. The slopes are getting smaller and smaller and smaller while it is still positive. Still, the slopes are still positive, still increasing. So this gets a little more challenging because now we have kind of two layers, right? We have the, well, three layers, right? We have the original function, We have f prime, and then we have f double prime. Both of the derivatives tell us something about the original function, but they tell us different things. Let's try an example then. Let's find where, let's look at our original function here that we started with. Even though it kind of messed me up when I picked it before, I'll give it a second chance. So find where this function is concave up. As soon as you see concavity, that tells you you need to work with the second derivative. So you don't have to overthink this part, right? Concavity means second derivative. So I find f prime of x, and then I find the derivative of that, which is going to be f double prime of x. Concavity comes from the second derivative either being positive or negative. So just like increasing, decreasing, where I want to know whether the first derivative is positive or negative, I need to find where this is zero or undefined. They're not technically called critical points because it's not where the derivative is undefined or zero, it's where the second derivative is undefined or zero, but they function in the same way. They're sort of where things are happening. So this is defined everywhere, so I don't worry about that. And I get x equal 1. What this is called is a potential inflection point. I should have written that out more clearly. Inflection. So an inflection point is where the concavity changes from either positive to negative or negative to positive, right? Up to down, down to up. That's called an inflection point. Now, I don't know if this is an inflection point yet. That's why it's called potential, because I actually have to see if it flips. But the same idea holds. This is my sort of one spot where the second derivative could change signs. So I'm going to divide my interval at that inflection, possible inflection point. And I'm going to pick a test point. Right, I just pick anything that I like that's inside the interval, and then I test it. Remember to test it in the second derivative. This inflection point goes with the second derivative, so it only makes sense to test it in the second derivative. Okay. This, of course, is very different than the numbers I got when I did the first derivative and the critical point. That has its own set of numbers. So here, when I put 0 into the second derivative, I'm going to get 0 minus 6, which is going to be negative. And when I put 2 in, I'll get 12 minus 6, which is going to be positive. So this is an inflection point at 1. And I also know where it is concave up or concave down, right? It's concave up from 1 to infinity, concave down from minus infinity to 1. On the graph, remember before I had these relative maximum and a relative minimum, I just know a little bit the way the cubic looks, so I was able to sketch it pretty well to start with, but this information here tells me that it's concave down as well all the way to 1. So that's where it's looking like this. All the way to 1. At 1, all of a sudden it switches, the slopes stop decreasing and they begin to increase again. It is certainly much harder to show that on a graph. The mins and maxes are pretty easy, right? Because it's just a flat spot. So it is nice if you're unsure or can't get it quite to fit on the graph for whatever reason, just make sure you put a dot there and never a bad idea to label the inflection points. Not as necessary when you have the mins and maxes, because the graph pretty much shows that. Questions about this problem at all? It's the same process overall, right? In that we find where it's 0 or undefined, we set up the intervals, we test the intervals. This part all looks the same, you know, whether it's the first derivative or the second derivative. But your conclusion and information you get is very different depending on which derivative you're working with. Together, this information gives us a really good sketch of the graph. Actual function values are. The shape of the function could have been this, or it could have been this, or this. This function could have been located anywhere on the y-axis, but the shape of the function has to be the same, right? I can't have it go down and up in a different spot because that's not backed up by the information there from the derivatives. Good question. We always have an inflection point? Definitely not. There are many functions that have no inflection points. You can have multiple inflection points. It just depends on the graph. So like, I mean, if your graph just looks like that, sorry, like a square root function, there's no inflection point there. It's always increasing and always concave down. You can also have spots where if you have like an x to the fourth or something like that, it will have a potential inflection point there, but it'll turn out to be concave up and concave up on both sides. So no inflection point there either. So, you know, certain types of polynomial functions will have inflection points and relative mins and maxes, but you're gonna run into a lot of different kinds of functions, and some of them will and some of them won't. So you just got to go through and test. Now, if there are no solutions to where the second derivative is 0, if the second derivative is never 0 or undefined, then you can't have an inflection point either, because the second derivative can't change sign. So, so that's another possibility. Lots of possibilities. Infinite possibilities, in fact. Right? So you've got to kind of work through this process each time if you're asked about either inflection points or concave up or concave down. Other questions?
Will the interval always be in between negative infinity and infinity?
That's a good question too. Not necessarily. So yeah, let's talk about that. Certainly, like you could have a square root function, like I saw in that case. You know, in that case, even if there was something like, you know, maybe you had something sort of combined with the square root function and it looked like this, then of course the smallest your interval could be, you know, then it might look like something like this, right? If you had a critical point there at 4, I just made up a graph. So your function may be restricted to a domain, and in that case, you know, your critical points would still fall and cut that domain into pieces, but the domain might not be minus infinity to infinity. Another thing that this kind of made me think about is if you have a function that has a, a vertical asymptote in it, this is not a continuous function, so we have to be careful about the mins and maxes and things, but this would show up as, you might think of this value, if we say that's -1, you might think of that value as a critical point because the derivative is certainly undefined there. But the function is undefined there too. So technically it is not a critical point, but it still could be a spot where the function could change from increasing to decreasing or vice versa. So we still have to check that because the derivative is undefined there. But this cannot be a relative minimum or maximum because the function is not defined there. And maybe an even better, maybe rather than this version, I should have shown you this version. So here, notice the function would go from increasing to decreasing. And so some people will tell me then that f of -1 is a relative maximum. And I will say you're wrong because the function doesn't even exist there. F of -1 doesn't exist. It's a vertical asymptote, so it cannot be a relative maximum or any sort of maximum. So there are some kind of subtleties both to like the domain and the conclusions that you get to make from the information you find. So this is also kind of connected to that idea of domain because here's a function who's missing some values in the domain. Other questions? Those are helpful. I think they help everybody, including me.
Yeah, thank you for explaining that.
Oh yeah, that's good. So I think, and the bottom line is there's a lot of variation out there. Each function has its own unique things, and so you've got to sort of work through the test and make sure you understand what the different things are telling you, right? The first derivative, the second derivative, the critical numbers, potential inflection points. They tell us a lot of information, but they don't tell us like everything, right? So we have to, be careful of some of these, I call them like edge cases, right? Like this is a classic one. Okay, the last thing I wanted to make sure to tell you, and again, I'm really, this is a pretty superficial treatment. You'll want to go back and look at some of the other examples in the lecture capture for sure to make sure that you see some more examples of the process, right? I'm trying to work at kind of a higher idea level here versus a lot of like solving equations and things like that, but that's certainly part of the challenge in the homework. You will also run across what's called the second derivative test. So just like the first derivative test, the second derivative test can tell us about critical numbers. So the first derivative test told us whether the critical numbers are relative maximums or relative minimums, and the second derivative test does the same thing, just using the second derivative. It tells us whether we have a relative maximum or minimum. And you might be, well, I'm hoping you're thinking, but wait, the second derivative wasn't actually critical numbers, right? He made a big point of that. Second derivative were these potential inflection points. It doesn't really have to do anything with relative maximums and minimums. And you're partially right there. The critical numbers, remember, are f prime of x equals 0 or undefined, right? That is true. Critical numbers are where the derivative is 0, undefined, and f of x exists, right, in the domain of f. So those are critical numbers. The first derivative test is a pretty good test almost all the time. But its one issue is that in order to make it work, I have to test the first derivative on one side and the other side of this critical point. And it doesn't seem that hard, but it can be a pain if there's like a whole bunch of critical points. I have to make sure I test kind of close enough to the critical point, and it sort of takes these two values and this comparison. So there are situations where a different test is easier, and this is the second derivative test. And what it says is, if we have a critical point, I defined it here, so I won't do it again, right? If we have a critical point and f double prime, let me call that critical point x equals c, because it's a critical point, and f double prime of c is positive, that tells me at the critical point that the second derivative is positive. It tells me that the slopes are increasing, and it actually forces us to have a sort of bowl-shaped situation. So if the second derivative is positive, we have to have this kind of situation, which implies we have a relative minimum. Be careful there. Sometimes people feel like this is a little counterintuitive because the second derivative is positive. Somehow maybe that feels like a max because it's positive, but no, positive means increasing, which means we have this bowl shape, and that generates a relative minimum. If it's negative, then we have like a hill shape, and that of course is a relative maximum. So this is actually really nice because, you know, if I check the critical point in the derivative, it's going to give me 0 or it does not exist. It's not going to tell me anything. But if I check the critical point in the second derivative, it could tell me the answer right away, whether it's a minimum or a maximum. So in a lot of ways, it's actually a very nice test. Well, there's two downers. Sorry to get your hopes up, right? But the one downer is if the second derivative is 0, the test is inconclusive, right? And in math, that's kind of the worst option. It doesn't tell us anything. It doesn't tell us it's not a min. It doesn't tell us it is a min. It just doesn't, I don't know. So that means I'd have to go back and check the first derivative. And we don't really love that relationship there. I don't like to do something where I don't know I'm going to get the answer, right? Because I'm going to put in some effort there, and if I don't know I'm going to get in the answer, then I'm like, is this going to be worth it? The second problem is that I need to use the second derivative, and that may or may not be that easy to find, right? Sometimes the second derivative is very easy to find, like with a polynomial. But sometimes, as you've seen already, the first derivative can be pretty messy. And if you have to take the derivative again, that can be a lot of extra work. So most of the time, the first derivative test is probably your best option. You will see a couple problems that require the second derivative test. So we do want to know how to use it. But I'm guessing most of you will probably use the first derivative test given the option. Going back to our old friend here, x cubed minus 3x squared minus 8x plus 5. Our critical numbers here, again, this is why I should have maybe redone it. I hate to have to reuse these bad estimated critical numbers, right? But they were a negative 1.1 and negative 3.1. Those are the critical numbers. And my second derivative was 6x minus 6. That was a second derivative that was really easy to find. And it's very easy to plug these in and see what I get. Oh, sorry, did I write that as a negative? That's a plus 3.1. So I put in a negative 1.1, that very definitely gives me a negative number, which is less than 0. Less than 0 means I have a relative maximum. And that's what we found, right, when we looked at the graph. When I put in 3.1, that's going to give me a positive number. Positive is a relative minimum. And again, that's what we found from the graph. Okay. So that information matches up with what we already knew about increasing, decreasing, and mins and maxes. But it's a different approach. It is nice to have different approaches because sometimes one approach is, we get stuck. We can't go forward for some reason, or we're missing some information. A different approach can save us from that. Okay. So in summary there from 4.3, the biggest and most important things are understanding that the first derivative tells us about increasing and decreasing, and the second derivative tells us about concave up and concave down. So that is number one and number two, right? Is figuring out those two things and those two parts. Once you have that information, that you really know about minimums and maximums as well, and that's what the first and second derivative tests tell us. Any questions, any follow-up questions to this or these concepts? Okay. In some ways, this is the most important section, I think, in chapter 4. There are some other sections that later on that do interesting things, but they're not they're not as rich as this section, meaning there's a lot of different parts of this that continue to show up for us. So maybe I say this with every section, right? But take some time to understand the concepts of this. It's very hard if you're just trying to follow along without understanding what you're doing, because there's so many different kind of layers and steps and combinations. But once you understand what you're trying to do, they don't have to be hard problems, right? So, okay. There was a question, maybe, if you're still there, from 4.2. If you have one, I can take a look at that. Otherwise, I think if you feel okay about things and don't have any other questions, I can let you go. And I'll see you on Thursday, right? Today's Tuesday. So hope to see you on Thursday. Remember, your 4.3 is due tomorrow night, so you need to be getting started on that. If you haven't already, get started on that immediately so that you can have some time to ask questions and get the help you need. You're all very welcome. Take care.
Thank you.
Yeah, of course.
Thank you.